Last month, I blood tested for the 7th time in 2025. And note that this is blood test number 65 since 2015. So with that in mind, what's my biological age? That's what we'll see here. This is using Dr. Morgan Levine's biological age calculator, PhenoAge. And when entering the data for its 9 component biomarkers, I get a biological age of 37.5 years, which is 15.7 years younger than the chronological. Now, at this point in the video, many people often ask, how good is this biological clock? If you want to see how good this biological age clock is or isn't, I made a video specific to that, so it'll be in the right corner. All right, so where can I improve? Because if I'm not trying to get better, at worst, I'll stay the same or get worse. So in the last video in this series, blood test number 6, I focused on the MCV, which unfortunately got worse for this test, so I won't go over the strategy again on how to fix that. I have made some changes that I think will impact MCV for the next test, so stay tuned for that story in another video. But for this video, I want to focus on glucose, which at 102 milligrams per deciliter is my highest value ever, 63 tests going back to 2015. But before jumping into that story, let's take a look at more data because this is just one test. It's important to look at the net of all tests over a given period of time as a true pace of aging. So with that in mind, for more context, I have 44 blood tests using this biological age clock since 2018, which is what we'll see here. This is year-to-year change for biological age, more specifically, using Dr. Morgan Levine's biological age calculator, PhenoAge. And this is from 2018 to 2025, and again, those 44 tests. Now, when I first started measuring in 2018 to 2019, and note that I've been collecting blood test data since 2015, but I wasn't measuring hsCRP at every test. So I started that in 2018 to 2019. So over 3 tests in a 2-year period, average biological age was 34.3 years. So then I started including hsCRP at every test, with 6 tests each in 2020 and 2021 for an average of 33.9 years in each of those 2 years. I then had my best data ever in 2022 at 32.1 years, and I also increased the testing frequency to 7 tests per year. Over another 7 tests per year in 2023, the average got a bit worse to 32.9 years, and then I increased the testing frequency to 8 times per year in 2024 with an average of 33.1 years, going in the wrong direction, albeit slowly. And then after the first 7 tests in 2025, we can see that average biological age is currently 33.7 years, which includes the most recent test of 37.5 years. So this is a true pace of aging. I know that there are other tests out there that claim to be a pace of aging, but a singular test may not represent a full year average, which then raises the question, how many tests per year do we need to have a true full year average? Maybe 8 tests isn't enough, but I think that's closer to the truth than 1 or a couple of tests per year. And this is how I'm defining a pace of aging. So with that in mind, there's good news and bad news. The good news is that I've resisted an age-related biological age increase using this test as that collection of 9 biomarkers that represent different organ systems. And that's important because even if all biomarkers stay the same, biological age using this test will increase by 0.9 years for every year of chronological age, such that my expected biological age using this test should be 39.7 years in 2025, whereas it's currently 33.7 years. So that's a 6-year reduction. So this is good news. On the other hand, I mentioned there's also some bad news. And first, we can see that all 6 tests after the first test in 2025 have moved in the wrong direction, which is not good news. Additionally, if we start the clock from 2022 at my best data, we can also see the trend line moving in the wrong direction, going with an age-related biological age increase. But here too, note that there's an expected biological age increase of 0.9 years per year, such that in 2025, starting in 2022, expected biological age using this test should be 34.8 years. So I'm currently 1 year below that. So the aging rate for these 9 biomarkers is still a bit slower, even though this is not my best data. All right, so let's review another example for studying the pace of aging and using glucose as an example because that's emerged as a major weak spot. And if I'm not trying to make that better, if I'm not trying to improve it, it's potentially going to get even worse. Also, how can I reduce glucose? And I'm going to show some data, but that's coming up just in a minute. So let's take a look at all glucose data for those 63 tests since 2015, with glucose plotted on the y-axis against chronological age on the x. So first, what's optimal? My reading of the literature is that 80 to 94 for blood glucose, fasting levels of blood glucose, may be optimal. But that's only part of the story. The other, and as I'm sure we all know, is that glucose levels increase during aging. So it's not just about getting your data into the optimal range, but also resisting glucose's age-related increase is the other half of that story. So where am I getting these data from? Well, I have a new Patreon tier dedicated specifically to what's optimal for biomarkers, including fasting levels of glucose. Besides glucose, it currently includes the 34 other biomarkers shown here, more than 2 hours of video content, 52 published references, and note that these aren't the reference ranges. This is what may be optimal based on my reading of the literature in the largest studies that exist. So if you're interested in that, check it out. All right, so back to the data. And if we look at all of my data over those 63 tests, average glucose is within optimal, 90 milligrams per deciliter. So technically I could stop there, just give it a check mark and it's all good. But there's more to the story. When I run the correlation for glucose versus chronological age, we can see that there is a significant correlation with a correlation coefficient of 0.33 and the p-value at less than 0.05 at 0.008. So here we can see I've been unable to resist the age-related increase for glucose, so we give that an X. If I stopped at just looking at the average, that would only be part of the story. It's important to look at all of the data within its full context. And here we can see that glucose is increasing within my data, so I've got to try to flip this sooner rather than later. And in terms of that flipping it sooner rather than later, we can see that 4 of the most recent tests have moved out of optimal. So I've got to find a way to move it back into the optimal and also resist the age-related change for blood levels, fasting blood levels of glucose, which then brings us to how can I reverse the glucose increase? So now we're going to take a look at diet versus glucose correlations. So how am I able to do this? For people who don't know, I've weighed almost all of my food since 2015 with a food scale. I then enter that data into a diet tracking app, Chronometer, and if you want to use Chronometer yourself, there's a discount link in the video's description. I then pull the Chronometer data into a spreadsheet, and then every blood test has a corresponding average dietary intake, such that if there's 50 days in between blood tests, by taking the average dietary intake over those 50 days and then lining it up with the blood test, every blood test now has a corresponding dietary intake. So I can look at correlations. With that in mind, let's take a look at the top of the correlations list, which is shown here. In the middle, we've got the correlation coefficient, lowercase r, and then to the right, we've got the p-value. And note that the threshold for statistical significance that I generally use is less than 0.05. So this is even more strict. This is the top of the list, less than 0.01. And if you want to see the full list, that's in the biomarker correlations tier on Patreon, which doesn't just include glucose, but all of the other biomarkers and their correlations with diet that I'm tracking. So if you're interested in that, check it out. So let's take a look at the list to see what I could potentially do to reduce blood levels of glucose. Well, atop the list is total fat. And I get that this may be opposite of what most people expect. Increased fat, lower carbs, and you'll end up with lower glucose. For that situation, generally most people eat high-carb diets, are eating pastries and cookies, and I understand that in those situations, glucose levels may improve. In my case, the diet is almost exclusively whole food based, with only cheat meals immediately following blood tests for 1 or 2 or 3 days, and then no cheat, no junk for 45, 50 days after blood testing. Nonetheless, let's take a look at the correlation for total fat with blood glucose levels as shown here. With glucose on the y-axis, plotted against the average daily fat intake that corresponds to each blood test on the x. And then when looking at the correlation, we can see that it's positive. So when my fat intakes have been relatively higher, that's been significantly correlated with higher glucose. And the opposite of that, when total fat intakes have been relatively low, that's been correlated with relatively low glucose. Now, for the most recent test, average fat intake was about 100 grams per day, and we can see where that data point lays on this plot. To get my data closer to that average of 90 that I've been able to maintain historically since 2015, the data suggests going closer to 88 or so, just below 90 grams per day, based on extrapolation of the trend line. So that's the plan for test number 8, which will be in December. So how well am I progressing on that goal? So average fat intake since the October 27 test, it's been about 3 weeks since the test, is currently 92 grams per day. So I'm not too far away from my 88 gram per day target. But note that total fat includes monounsaturated fat or MUFA, omega-3, omega-6, and sat fat. So that doesn't really, just because I have a correlation with total fat, it doesn't tell me which of the fats that I should potentially reduce to potentially improve blood glucose levels. So sat fat is indeed on the list, and in my case, sat fat has been on the lower side of my range, almost close to the lowest side, as I've been testing the effect of lower sat fat on cystatin C and B2M. Both of those came down, so lower sat fat in my case may be a part of keeping those two biomarkers low, but when considering it was already on the lower side, it may not be a significant contributor to why glucose levels were 102 for this test and 96 for the test before that. But then note that monounsaturated fatty acids, or MUFA, are also on this list and a positive correlation. So let's take a look at those data, which is what we'll see here, with again glucose on the y-axis plotted against the average daily MUFA intake on the x. Now for test number 7, we can see that my MUFA intake was actually the highest it's been over the past 10 years, around 42 grams per day. And note that in terms of where I'm getting my MUFAs from, the major source for this test was avocado, 8.5 grams per day, olives, not olive oil. I'm a whole food and no oils type, so I'm eating olives, not olive oil, 8 grams of MUFA per day for this last test, almonds, 6 grams per day, and sardines, 4.5 grams per day. So this is the majority of my MUFA intake for this test. So based on extrapolation of the trend line to get me closer to that 90 milligram per deciliter average target, and I get it. Some people are probably saying you should go even lower, go to 85 or 80. I agree with that, but progress first, albeit not perfection. So based on extrapolation of the trend line, having MUFA intakes closer to 20 grams per day may get me to that 90 milligram per deciliter target. So how well am I doing to that means, to that end? Well, average MUFA intake since the last test on October 27th is currently 27 grams per day. I'm not at the 20 gram per day target yet. I'm working my way there, but 27 grams is a big cut relative to 42 grams. So here too, progress, albeit not perfection. But when it comes to the correlations, I try not to just follow one or two, but as many as possible, as I don't know the recipe for impacting the biomarkers. I may have to move the needle for diet with 5, 6, 7, 8 correlations in order to get an effect on a given biomarker. So with that in mind, note that protein intake is also on this list. So let's take a look at that plot. That's what we'll see here. So on the y-axis, we've got glucose, and then on the x-axis, now it's average daily protein intake. We can see the trend line. So here too, higher protein, that's significantly correlated with higher glucose, and vice versa. Now for this test, average protein intake was 125 grams per day, and we can see where that data point lays on the overall plot. But to get me closer to 90 milligrams per deciliter based on extrapolation of the trend line, these data suggest that being closer to about 108 grams per day may be what I should be doing for test number 8. So with that in mind, average protein intake since the October 27th test is currently 109 grams per day, not too far away from the target. But I'm not stopping there in terms of following the correlations. I intend on following all of the correlations on this list. I want to get my glucose levels back to optimal sooner rather than later. In terms of the other correlations, note that sodium is there. That's a positive correlation, which suggests that I should cut my sodium intake. And note that I've been doing the sodium experiment to see if it impacts HRV and resting heart rate, but also potentially hair graying. And if you missed that video, I'll link to it in the right corner. So for test number 8, thus far, I've cut sodium intake by 400 milligrams per day, which follows the correlation. Positive correlation suggests that too high may be bad for glucose, so I've made a cut, which should be potentially good for glucose. How good for glucose? We'll find out. I've also cut calcium intake. That too has a positive correlation, 80 milligrams per day, but that's a relatively minor cut, may not make much of a dent. I've also increased fiber intake. We see that that's a significant inverse correlation. So that suggests that when fiber intakes are at the higher end of my range, that's significantly correlated with lower glucose. And thus far, it's only about a 5 gram per day higher intake of total fiber. And I'll be trying to push that a bit higher over the next few weeks before the next test. We can also see vitamin D is on the list there too, in inverse correlation, but I'm not following that correlation, at least not yet, because I've been getting the majority of my vitamin D production from sunlight with 20 minutes per day of whole body sun exposure, as I now live in a warm weather climate, Austin, Texas, where I can do that almost daily. But we're almost towards the end of November and it's going to get very difficult to do that, so I'll probably have to start vitamin D supplementation, at least 1,000 IUs per day, maybe 2,000 like I was doing in Boston. So stay tuned for that to see how it impacts circulating levels of vitamin D. We can also see a significant inverse correlation for net carbs. So to follow that correlation, I've increased it by 46 grams per day. So a bit less fat and a bit more carbs following the correlations. And then last but not least on this list is beta-cryptozanthin, which I get almost exclusively from red bell pepper, but also more recently, butternut squash, a small amount of butternut squash per day. And to follow this inverse correlation, I've increased it by 700 micrograms per day, which is about a 50% increase over where it's been historically. So whether the net effect of all of these, following all of these biomarker correlations will impact glucose, we'll have to wait to see for the next test. In terms of when that test will be, it'll be on December 15th, 2025. That's the scheduled date. So if you want to see those data, I post it immediately on Patreon, and then it takes me a few weeks to make the video there too. First posted on Patreon before posting it on YouTube about a month later. So this is just part one of this video series after every blood test. Next, we'll take a look at the full blood test report, and then in the video after that, we'll take a look at diet, supplements, and prescription meds that correspond to this 16-year younger biological age. If you're interested in more about my attempts to biohack aging, check us out on Patreon, where I offer blood test consults and also post at least twice per day in 4 other Patreon tiers. We've also got a whole bunch of discount and affiliate links that you can use to test yourself that help support the channel, including ultralabtest.com, which is where I get the majority of my blood tests done, the clearly filtered water filter, which I use every day, at-home metabolomics, oral microbiome composition, NAD testing with Ginfinity, epigenetic testing with True Diagnostic, at-home blood testing with SciFox Health, which includes GrimAge, the best epigenetic clock of epigenetic clocks, green tea, diet tracking with Chronometer, or if you'd like to support the channel, you can do that with the website Buy Me a Coffee. We've also got merch, including Data is my North Star, Figuring Stuff Out is my drug, and the ConquerAging or Dietary logo as shown here. Link in the video's description. Thanks for watching. I hope that you enjoyed the video. Have a great day.